In this lecture, we are dealing with very much realistic type of situation where there are multiple masses on multiple plane. Previously, we started with the single mass on a single plane, then multiple masses on a single plane. Now, a very realistic situation is the masses will be distributed on number of planes. So this lecture is all about multiple masses on multiple planes and how to balance these unbalanced masses. So there are multiple rotating planes, and on each plane there is a unbalanced mass. Maybe these rotating planes represent gear 1, gear 2, gear 3, and all these gears are mounted on a single shaft. Maybe these rotating masses, they are representing some like pulleys, pulley 1, pulley 2, pulley 3, or whatever you can think about. So these multiple rotors can represent any of the system. However, on each plane there is a single unbalanced mass. For example, if there are three gears on a single shaft, gear 1, gear 2, gear 3, and each of the gear, one of the teeth is broken. So teeth is broken, there is some unbalanced mass, teeth is broken, some unbalanced mass, teeth is broken, some unbalanced mass. So you can think about different scenarios. The schematic diagram of this system can be represented by top figure and the bottom figure. Both has merits and demerits. For example, the top one, we can see the mass m1 at some radial distance r1, mass m2 at some radial distance from the axis of rotation, mass m3 at some radial distance from the axis of rotation. So this one line, the blue line, represents axis of rotation. Here is the axis of rotation. Also, the distance between the axial distance between mass m1 and m2 can be obtained here. Axial distance between mass m2 and m3, and similarly axial distance between mass m1 and m3 can be seen. The only drawback at the top figure is we can't see the angular position of mass. So in the bottom we can see the angular position. For example, if you assume the mass m1 is on a horizontal axis and the force produced by this unbalanced mass f1 can be represented by fm1. The fm2 is at some angular position with respect to horizontal, and it will be angle theta 1. And the force produced by this unbalanced mass m2 is fm2. The third and the last is the mass m3 on plane 3, and it is at some angular position with respect to center of axis or axis of rotation. So angle theta 2 is the angular position of m3 with respect to horizontal, and the force produced by this m3 is fm3. To balance the unbalanced system of unbalanced masses on multiple planes, the best scenario is that we can choose some balancing masses at some arbitrary planes at some radial distance from the axis of rotation. So the blue line represents axis of rotation, and also at some axial distance at the axis of rotation. To balance the unbalanced forces in case of multiple masses and multiple planes, there are a few considerations that we have to keep in our mind. The first consideration is that we have to balance the forces and balance the couples. Couple is nothing but the moment. At first we have to balance the couples. In balancing the couples, what we are doing, we have to choose an arbitrary plane in a way that it will cancel the couple produced by one of the balance mass. Because in our scenario we know the mass m1. If we know the mass m1, r1 is known, then we can have a known value of fm1. Also mass m2 is known, the radial distance from the axis of rotation. The radial distance from the axis of rotation is known, therefore fm2 is known. Mass m3, the unbalanced mass m3 is known, and the radial distance from the axis of rotation is known, therefore fm3 is known. The only unknowns are the balance masses b1 and b2. In case of couple, what will happen that the force produced by m1, which is fm1, has to be multiplied by the axial distance, such as this. So couple C1 is the force produced by fm1, the mass 1, into the axial distance L1. The couple at B1 will be 0 because this B1 is chosen as arbitrary plane where all the moments of couple will be taken. Therefore, movement around its own plane is 0 because there is no axial distance. As you can see, in case of M1 the axial distance is L1. In case of B1 there is no axial distance because this plane is taken on B1. By this way, one of the balance force is, we are getting it away from our system. Away from our system doesn't mean that it doesn't exist. Away from the system means that in calculation we can avoid B1. Then couple C2 is produced by force of unbalanced mass m2, which is fm2, into axial distance L2. Then force produced by the balanced mass b2, which is fb2, into the axial distance L3. And the last couple is C4, which is the force produced by mass, the unbalanced mass m3, which is fm3, and the axial distance L4. So here are the couples. Secondly, what we are doing, we have to draw a polygon very similar to the polygon drawn for the multiple masses on a single plane. So for the couple polygon, what we will do, we take a suitable scale and we equate the scale to the magnitude. For example, there will be some magnitude of couple C1, so we will equate this to the scale. For example, couple will have some magnitude 100, then we say that 10 is equal to 1 centimeter. So by this we will draw a arrow, and the magnitude of arrow represents the magnitude of couple C1. As you can see, the couple C1 is on horizontal, so there is no angle theta. The angle theta 1 is for the couple produced by mass m2 or fm2, and the angle is theta 1, and the magnitude of couple 2 is represented by arrow start from here, ends at there. The third couple is C3. In case of C3, the magnitude of couple C3 is represented by this arrow. Start from here, ends at there, and the angle theta is theta 2 from the horizontal. So to close the polygon, we will draw an arrow which will meet tail to the first arrow and end of the last arrow, and this, the magnitude of this final arrow which is closing this polygon, represents the magnitude CB2. So by this means we will know the magnitude of couple CB2. If magnitude of CB2 is known, then we can find the mass B2. RB2 is already known, L3 is known. The only unknown is mass, the balancing mass B2. If all the others are known, so what we'll do, by CB2 is known by this polygon method. We divide the magnitude CB2 by RB2 into L3. So what we'll get? B2 is now known. Next, we will draw a force polygon. In case of force polygon, the additional force is from the mass, the balancing mass B2, which is FB2, because if the balancing mass B2 is known, the radial distance RB2 is known, then we can easily find, we can easily calculate FB2. So FB2 is known in our situation because we already have calculated mass B2. From this mass B2, FB2 can be easily calculated. So in case of force polygon, we will draw in a scale. We will draw the scale, and by this scale, for example, this arrow represents the magnitude of FM1. Then this arrow represents the magnitude of FM2 at certain angle theta 1. Then the arrow here represents the magnitude of force FM3 at the angle theta 2. Start from here till end here, start from the horizontal, end it here. Then comes the balancing force FB2 represented by the blue arrow. So it's at angle theta B2. To close the polygon, we have to draw an arrow which will meet the tail of the final arrow will meet with the tail of the first arrow, and head of this arrow which is closing this polygon will meet the head of final arrow. So we will measure this distance from tail to head. It will be the magnitude of FB1. So if FB1 is known, RB1 is already known, the distance, the radial distance of balancing mass B1 from this axis of rotation. Then we can easily calculate the unknown mass, the balancing mass B1. Just divide FB1 by RB1. So by this way, we can easily calculate the unknown unbalanced mass B1. To clear any ambiguity, let's do an example. And this example is problem based, and the problem is taken from the real life situation. So at the bottom you can see there are 3 gears. They are mounted on the same shaft, and each of the gear has some defect. Maybe the teeth is broken, or maybe there's some casting defect such as blowholes. And because of these defects, there are unbalanced masses. For example, gear 1, the unbalanced mass is of 200 gram. Gear 2, the unbalanced mass is 600 gram. Gear 3, the unbalanced mass is 100 gram. The radial distance from the unbalanced mass to the central, the axis of rotation is 5 cm. In case of gear 2, the radial distance from the unbalanced mass to the axis of rotation is 6 cm, and the radial distance between the unbalanced mass to the axis of rotation is 7 cm. Also, the axial distance between the gears are known. All are represented in the centimeters. Other very important information is the angular rotation. So angular position of each of the gear is known. If we take the gear 1 as a horizontal, then the unbalanced mass on gear 2 is at the angle of 45 degree with respect to horizontal, and the angular position of the mass 3, which is 100 gram, is at 90 degree angle with respect to horizontal axis. Next, what we'll be doing, we will choose two masses, the balancing masses, at two arbitrary planes. The first plane is A, the second plane is B. The radial position of balancing mass B1, which is at plane A, is known, which is 4 cm, and also the axial distance from the gear 1 is known, which is 10 cm. Similarly, at plane B, the second balancing mass B2 is placed, which is unknown. However, the radial distance from the axis of rotation, which is 3 cm, and known, and also the axial distance from the other gears are also known. The only unknown here are the balancing mass B1 and balancing mass B2. So how to deal with the problem? So we can formulate a table where we can present the plane 1, plane A, plane 2, plane B, plane 3, mass, the known 200, B1, the balancing mass B1 is unknown, the balancing mass at gear 2 is known, which is 100 gram, balancing mass at plane B is unknown, and the last gear, gear 3, the unbalanced mass is 100 gram. The radial distance of each of the balanced or unbalanced masses are 5, 4, 6, 3 and 7 cm. The axial distance are -10, 0, 10, 20 and 30. Why there is 0? A very critical information was shared in the lecture that we can choose, in case of movement, we can choose a arbitrary plane around which we have to take a couple or movement. So in this case, we have taken an arbitrary plane at plane A, and all the movements of other gears is taken around A. Interestingly, if there is a couple or movement of plane A, plane 2, 3 and this plane B, the direction will be, for example, if there's a movement of this unbalanced mass at gear 1, it will be, for example, clockwise. Then the movement of couple of remaining masses will be counterclockwise, because they are on the other side of this arbitrary plane. I will repeat again. If we take the couple or movement of this gear, this unbalanced mass at gear 1, which is 200 gram, if this is a clockwise direction, then the movement or couple produced by the other balanced or unbalanced masses will be counterclockwise direction. That's why I use -10 with the axial length, so that at the final, when we calculate movement, it will be negative. So negative represents clockwise direction and the positive represents counterclockwise direction. Or you can say that this arbitrary plane where we are taking the movements from left hand side, whatever it is, it will be taken a minus, just as this, -10, and the right hand side are taken as the positive sign. Because we are taking the movement around this arbitrary plane A, then we are counting this axial distance 0, because there will be no movement, and by this we are getting rid of this balancing mass B1, not physically but in calculation. Similarly, distance 10 is the distance from this arbitrary plane from this gear, the unbalanced mass as gear 2. Then 20 centimeter is the distance from the arbitrary plane to the balanced mass B2, and the last one is 30 centimeter distance is the unbalanced mass of 100 gram at gear 3 with respect to arbitrary plane. Force can be calculated by multiplying mass with the radius. So we calculate 200 into 5 is 1000, B1 into 4 is B1 into 4, 100 into 6 is 600, B2 into 3 is B2 into 3, 100 into 7 is 700. Couple can be produced or can be calculated by multiplying force into axial distance. Here's the force, here's the axial distance, 1000 multiplied by -10, 10,000, and with the minus sign. B1 into 4 multiplied by 0 is B1 into 4 multiplied by 0. So this couple will be equal to 0. Then 600 multiplied by 10, it will come 6000. B2 into 3 into 20, so B2 into 3 into 20. 700 into 30, it will come 21,000. So our table is completed. Now we'll draw first couple polygon and then a force polygon. By couple polygon we will know the B2, and then a force polygon we will know the B1 also. So by this means we will get the balancing masses and our problem will be solved. As I already mentioned, so what we are doing here, we are drawing a scale. So in this case, in case of couple polygon, these one increment mean one box movement is equal to 2500 gram per meter square. So unit of couple is gram centimeter square. So one movement is, or one box movement is 2500 gram per centimeter square. So in case of first we have to draw a couple of -10. So the direction of this couple will be in negative direction, and the magnitude will represent the magnitude of couple, but according to the scale. So we can move 4 boxes. If we multiply 4 into 2500, it will come 10,000, but in minus direction, negative direction, so we are going this direction, in the left hand side direction. Next is the magnitude of couple 6000. So this 6000 is, if we divide this 6000 by 2500 or 2500, then we can move this magnitude at an angle of 45. So this magnitude is equivalent to 6000 gram per centimeter square. Then comes the couple produced by FM3. So here's the couple and the magnitude is 21,000. So this magnitude represents 21,000 at an angle of 90 degree with respect to horizontal. Then at the end we will combine or close the polygon by combining the tail of resultant with the tail of first and head of resultant with the head of last arrow. So this arrow now represents the magnitude of couple. Which couple? CB2. So B2 multiplied by 3 into 20 is equal to 11.3, which is the magnitude of this arrow, And how much is the magnitude? Multiply by 2500, because each increment or each block represents 2500. So we have to multiply the length, which is 11.3, 11 boxes and 0.3 more, into unit, the scale unit, to have 2500. So by dividing the remaining 3 into 20, which is 60, if we divide this 60 to this, we will get 471 gram. So mass B2 is now known. The only unknown is left, which is B1. Please note that we also, by this polygon method, we also know the angular distance, or the theta of this B2, which is at 115 degree. Now, when we know the magnitude B2, which is 471 gram, we have to draw another polygon. So we start from the FM1. This represents the force FM1, and this is according to scale, means one increment is equal to 400 gram per gram meter. So 400 gram meter means here's the force 1000. So we can move 2.5 boxes. So 1 box, 2 box and a half box, and the angle is 0 degree. Then the second one is force FM2 at an angle of 45, and the magnitude is 600. So 600 means 1.5 box. So 1.5 box at an angle of 45. Then comes the force produced by the FM3, which is 700. So 700 means that we have to move nearly 2. So at the angle of 90. So we will move nearly 2, but not full, because it's 700, a little less than 2. The last one is the magnitude of the magnitude of force FB2, which is a product of mass B2, which is 471, calculated from the couple polygon, and we have to multiply it with the radial distance 3. We will get the final 1413. So we have to move magnitude 1413 according to the scale. So if we move at an angle of 115, so here we get it here. To close the polygon, we will draw an arrow from which meet at the tail of first and head of last. So the magnitude of this arrow represents force produced by the unbalanced force, the balanced force, the balanced mass B1. So B1 into 4 is the force produced by the balanced force B1. It's equal to 6.5, which is the magnitude from here till here, and because we are taking the scale, so we have to multiply 6.5 into 400 to calculate B1. Keep the B1 at one side and remaining numbers at the other side. We will get 650. So here we are. So we have calculated B1 also. All the numbers are known to us. To balanced masses, unbalanced masses, and their angles. The final B1 is at angle of 62 degree. So our problem is solved. So that's how you can solve the multiple mass on multiple plane problem. If you have any question or query, then you can ask via WhatsApp group or some other social media such as Facebook or Google Classroom. Thank you for paying attention. Thank you.